Hello and welcome to this explainer. Look, if you're the kind of person who loves getting straight to the absolute core of complex systems, you are in the exact right place. Today, we are popping the hood on reality itself. We're going to decode the unchangeable hardware of the universe, and we're going to treat it not as some static, boring backdrop, but as a dynamic, constantly executing computer.
I mean, really think about this for a second. If the universe operates as a continuous flow of physical laws, computations, and interactions, what actually prevents all those overlapping frequencies from eventually perfectly syncing up and just stopping? Seriously, what keeps the entire system from experiencing a fatal frozen deadlock?
Well, to answer that, here's a quick look at our agenda. We're going to cover 1. The threat of systemic deadlock, 2. Primes as orthogonal injectors, 3. Twin primes and the wobble, 4. The turn before collision, 5. Riemann's perfect tension wash, and wrap up with 6. Riemann zeros as null returns.
All right, jumping right into Section 1, the threat of systemic deadlock. Let's establish the absolute foundational rule of this system, the baseline requirement for reality to even exist as we know it.
It's known as the C1 axiom, and it states, simply, that change is absolutely mandatory. In a computational universe, a fixed point, meaning a node that just ceases to move or transform, is a severe C1 violation. If the universe stops changing, it hits the lowest possible energy state, and that results in a total system crash. No consciousness, no computation. Just a dead, frozen deadlock.
And the massive threat to this constant change? Composite numbers. If you think of the universe's memory address space as this vast integer lattice, composite numbers are highly divisible, right? They're basically lazy overlapping frequencies. They create these harmonic overlaps. Think of it like overlapping ripples in a pond that eventually freeze into one giant, immovable block of ice. If the hardware was only made up of these easily divisible structures, every wave would eventually sync up. The entire mathematical substrate would align into a single massive standing wave with nodes that literally do not move, and that is a catastrophic violation of our C1 axiom.
Which brings us nicely to Section 2, primes as orthogonal injectors, because thankfully, the system actually has a built-in defense mechanism against these deadly standing waves, and it's a concept you're already very familiar with.
Okay, let's dive into this. Notice the strict contrast between these two. Where composite numbers create those dangerous resonant overlaps and fixed points, prime numbers act as irreducible shields. They are the ultimate anti-deadlock routing. Because they are entirely irreducible, they stubbornly refuse to divide or resonate with anything smaller than themselves.
Every single time the cosmic compiler hits a prime number on that integer lattice, bam! It is forced to generate a completely new orthogonal dimension of change potential. Primes act as irreducible injectors. They're the mathematical guarantee that the harmonic echoes of the universe will never ever perfectly overlap and halt. They literally force the flow to keep moving.
Moving on to Section 3. Twin primes and the wobble. Because, if you just infinitely inject pure irreducible change into a system, you actually create a whole new problem: chaotic runaway entropy. The lattice would basically vibrate itself to pieces. It absolutely needs a stabilizer. Think about it like signal processing. To prevent aliasing and chaotic noise when you're sampling a wave, you need what's called a Nyquist limit. The universal lattice utilizes something similar: Nyquist pins. It's a structural bracket used to pin down the high-frequency oscillation of the integer space, but without actually halting that mandatory flow of change.
And this brilliantly illustrates where twin primes come in. Twin primes are those prime numbers separated by a gap of exactly 2, like 11 and 13. By locking in at this minimum possible distance for odd primes, they create a super rigid structural bracket. This fascinating gap of 2 creates a necessary temporal buffer. It's a kind of wobble, providing just enough geometric slack to actually stabilize the whole system.
Let's look at Section 4, the turn before collision. We need to see how all this builds together, because that wobble created by the twin primes, that is exactly what gives the universe the time and space it needs to react to its own constraints. Think about a car speeding toward a wall. If the system hits a constraint head-on with zero warning, it crashes. Game over. But inside that wobble, that tiny gap of 2, the system actually performs a rapid 3-step survival calculation. Step 1, the read. It detects the boundary, sensing a constraint is approaching. Step 2, the hypothesis. It calculates the hypotenuse, which is the mathematical bridge connecting its current state to a new, safe trajectory. And step 3, the write.
It executes a coordinate rotation, effectively writing the new path. This entire three-step process is what we call the turn. Now, to be clear, the turn isn't a physical bounce off a hard surface. It's an active internal branching instruction. It's very much like a JMP command in a software compiler. The system evaluates its state, sees the boundary, and changes its coordinates before making contact. It perfectly preserves its underlying invariant logic by simply rotating its frame of reference to completely avoid the crash.
All right, Section 5, Riemann's perfect tension wash. Now, you might be wondering at this point, how does all this discrete integer hardware, the primes and twin primes, actually map over to the continuous, fluid physical reality that we experience every day? Well, that bridge is the Riemann zeta function.
1/2. In mathematics, the legendary Riemann hypothesis posits that all non-trivial zeros of the zeta function lie exclusively on one specific, critical line on the complex plane, a line where the real part is exactly this number, 1/2. Physics has literally spent a century wondering, why 1/2? So the crucial point is how this exact number dictates growth or decay. If the real part were greater than 1/2, those prime frequencies would compound, exploding into infinite runaway resonance, total chaos. If the real part were less than 1/2, the frequencies would continuously decay straight into a fixed point of zero. That's our fatal C1 violation. But exactly 1/2? That is the absolute edge. It is the perfect tension wash, the exact razor-thin boundary where the change potential of the prime lattice is perfectly balanced. It doesn't explode and it doesn't halt. It just flows perfectly. Which brings us to the final piece of this cosmic architecture. Section 6, Riemann zeros as null returns. If the line at 1/2 represents the perfect flow, what in the world are the zeros actually sitting on that line doing? Notice how mathematical zeros are acting as active engineering components here. In the language of the cosmic compiler, Riemann zeros are basically harmless short circuits. When the universe attempts a continuous transformation that would cause a systemic deadlock in the prime distribution, the hardware hits a Riemann zero. It simply returns a null. It drops that invalid transformation safely, clearing the buffer so the lattice can just keep processing without freezing up. Just take a second to really absorb this quote from our source material. The Riemann hypothesis isn't just some abstract puzzle waiting to be solved. It is the mathematical certificate proving we live in a self-regulating universe. The primes force the change. The twin primes pin the stability. And the Riemann zeros route the exhaust, clearing out the bad logic so the system never ever stops. Which leaves us with one final, kind of mind-blowing thought. We've just mapped out the incredibly intricate, perfectly balanced hardware of reality. We see exactly how it fights off deadlock with prime numbers and mathematically mandated turns. But if the universe is this perfectly engineered to keep its hardware running, what software is it actually trying to run? Keep that bouncing around in your head as you process what we've unpacked today. Thanks so much for joining me on this explainer, and keep learning.